It's a good time to start. So, hello everybody. Welcome to the final day of the Satisfiability Bootcamp. So today we have three amazing speakers. The first one is Kuldeep Meal, who will be talking about approximate counting and sampling. The second one would be Nikolai Bjorner, who will be talking about SMT solvers. And the third is Ruzikcha Piskach, who will be talking about applications of SAT in formal methods. And each talk is going to be about 50 minutes long, followed by around 10-minute questioning and break. So allow me to start by introducing Kuldeep. Kuldeep is currently an assistant professor, Sung Ka K, assistant professor in the computer science department at the National University of Singapore. He's also a long-term visiting professor at the computer science department at IIT Bombay. Kuldeep is already a very prolific researcher. He's a recipient of many awards, including the AI's top 10 to watch by IEEE Intelligent Systems in 2020. So without further ado, the online forum is yours, Kuldeep.
Thank you, Vijay. And thanks to the organizers for inviting me for the bootcamp. Okay, so let's get started. As it's the norm that I'll be presenting work that I had opportunity to do with a lot of collaborators. So I would really like to acknowledge them, and special shout out to Mate Sus, who has been maintaining these counters and samplers that I'm going to talk about. So I guess in the first 4 days of the boot camp, at this point, all of us could agree that modern SAT solvers are really able to handle problems that were probably unthinkable just about a few years ago. And as we have seen, these solvers find application in wide variety of domains. And motivated by this, some of us think that now that SAT is easy. Of course, I'm putting it in quotes, but it seems to be easy for problems that arise from practice. It is time to look beyond satisfiability. So what problems beyond satisfiability I'm talking about? Well, we have a set of Boolean variables, x1 to xn, a formula over these variables. Let me introduce a little bit of notation here. I'm going to call sol of f as the set of solutions of this formula. So the problem of satisfiability was to ask, is this set empty or non-empty, right? Well, now we can start talking about properties of this set. For example, we can ask how many elements are in this set. Ask this question to estimate it exactly, or maybe a little bit approximation. So we are going to be looking at what is called epsilon delta approximation, which is that the estimate that we get is within 1 plus epsilon factor of the exact count with confidence at least 1 minus delta. Another problem that is usually related to counting is of sampling. So in this case, we are interested in designing a technique so that it is going to output one of the solutions, and the probability wise output is 1 over the number of solutions of the formula. Again, we'll allow some approximation, in particular what is called almost uniform sampling. So in this case, the probability wise output is within 1 plus epsilon factor of the ideal uniform probability. Let me give a quick example to make sure we are on the same page. So here is the formula f, x1 or x2. There are 3 solutions to this formula, essentially all the values of x1, x2 except 0, 0. The number of solutions of this formula is 3. So a counter is supposed to give an answer 3. A sampler is supposed to sample each of these solutions with equal probability, that is 1 by 3. I hope we are on the same page here. If there are any questions, feel free to unmute or ask during the talk. That would be much better. Okay, so at this point, one question that we might ask is, why are we interested in these problems? Well, it turns out not only there are fundamental problems from theoretical computer science perspective, but they also find wide variety of applications, ranging from network reliability, hardware validation, and so on. Today, I'm not going to talk about applications per se, but I'll be happy to chat about this after the talk.
So Kuldeep, there is a question by Jakub Nordstrom on your
Yes.
chat. Can you see it?
Uh,
So the question is, in uniform sampling, would
yeah.
it be acceptable to fail to output a solution with some small probability, or in the applications you always need some solution?
Yeah. So in case of uniform sampling, it is okay if with some small probability the sampler does not output a solution. You can just rerun it. And in fact, the sampler that I'm going to talk about will not, there's a small probability of failure in theory. Yeah. Okay. I'm going to keep track of the chat now. Thanks. Okay. So, well, you remember that I told you that set is easy, but it was in chords. And we are going to look at designing techniques that are going to build on top of this really impressive progress in set. But it's all going to be, these algorithms are going to be designed. And when we are designing these algorithms, we have to look through the lens of set revolution. And there are few things that one needs to take into account. The first is set oracle is not NP oracle. Why so? Well, normally most of the state of art set solvers, if they return unset, you get a proof with it. If there's a, and instead of a decision oracle, the solvers, whenever a formula is satisfiable, they are going to return a satisfying assignment. That makes a bit of difference because in case of NP oracle, you would say that getting an answer is only a, um, just one call, but getting a satisfying assignment would require you n calls. But in case of set, it's just one call. If the formula is satisfiable, then you get a satisfying assignment for free with it. More importantly, the set solvers are not set oracle. Why so? Well, the performance of these solvers depends on the formulas you give to them, and it's going to be very important as we design techniques. I'm going to tell you that, well, the two queries are can be queried to an oracle, but we are going to prefer one over the other simply because set solvers are going to work well on one of those queries, even though they might have the same size. And the third part that becomes critical is memory fullness. What do I mean by that? Most of the solvers today support incremental solving. In particular, if we have to formalize f and g, it's often easier to solve f followed by g if somehow g could be written as f and h. Why so? Well, since the solvers depend on series close learning, so whatever clauses we learned while solving f can still be reused. So we are going to uh, design techniques where if it would be possible, we can have two queries followed in a way that we have f followed by g, so that g is constructed by adding more constraints. I'm going to tell you that these are good queries. So I'll keep coming back to these three observations as we design these algorithms to motivate or to argue why these the algorithms that we are designing are preferred over the alternatives. Okay. Okay, so let's get started. First, I'm going to talk about constraint counting. I'm going to describe a framework called hashing framework. And there has been a lot of work in past 15 years over it. Uh, and we are going to see how we can apply it to do counting. And then in the second half of the talk, I'm going to move to talking about constraint sampling. So if we get started, and if all of us were in Berkeley, a simple question to and a nice question to wonder about would be how many people in Berkeley like coffee. I just googled before the talk. It looks like the population of Berkeley by Wikipedia is 112,000. We can assign everyone a unique 17-bit identifier. So how would we go about figuring out how many people in Berkeley like coffee? Well, one technique one could do is, let's pick about 50 people. We count how many of them like coffee and we can scale the count. If you think about it, is this always going to work? Perhaps not, right? What if there are only 5 people who like coffee? And in this case, it's unlikely that we'll find anyone who likes coffee in our sample of 50. So we'll give a really bad answer. Or if we find somebody in our sample, then we'll again give a very high answer. So the technique is probably not going to work. And this is where it would be nice to be able to use the power of set solvers. So a set query that I'm going to, by analogy, argue is find a person who likes coffee. If there are only 5 people, a method can be find a person who likes coffee. Then you ask for the second person, find a person who likes coffee, and the person not person Y that you just found. You can make such queries. In that case, if there are only 5 people, you'll make 5 queries, and that's your counting algorithm. Is this a good algorithm always? Probably you will agree with me that not really, because there can be exponentially many people who like coffee. And in that case, we'll be making 2 to the n queries. So n is the number of variables, 2 to the n is the number of possible uh, solutions here. In this case, the number of people who like coffee. In case of a formula, these are the solutions to the formula. So the important consideration here is that can we do with lesser number of set queries, possibly linear or logarithmic, and we'll see how far we get along. So how does these techniques work? Well, consider the circle to be the space of all possible assignments, and the dots here represent satisfying assignment. Since we cannot enumerate all the solutions, wouldn't it be nice if we could partition the space of solutions into cells that are roughly equal and they are small enough? What do I mean by small enough? Well, if I go and pick one of the random cell, then I'll be able to enumerate all the solutions in the cell. If I can do such a division, then the algorithm would be go and pick a random cell. Since we can enumerate all the solutions, we enumerate all the solutions in this cell, we figure out how many we found, and then we are going to multiply by the total number of cells. So what are the challenges for this technique to work well in practice? One thing that we need to answer is how are we going to partition into roughly equal small cells of solutions without knowing the distribution of solutions? There are 2 more challenges that are going to be critical as we go along. One of them is how many cells do we partition into? The third challenge is what is exactly a small cell? How do we characterize what we call as a small cell? So let me start discussing the first challenge, which is how do we partition into roughly equal small cells without knowing the distribution of solutions, right? If you knew the distribution, then the problem would become much very simple. So what we are interested in doing here is to design a function that maps assignments to cells. So once we have such a function, then solutions in a cell alpha is just the conjunction of the solutions of the formula conjuncted with all the y that H maps to alpha. A deterministic hash function is unlikely to work, so we rely on randomization. In particular, we choose a hash function randomly from a large family of hash functions so that such a hash function can partition into roughly equal small cells with high probability. This is, of course, a very classical notion of universal hashing proposed by Carter and Wegman in their seminal work in 1977. In particular, these techniques, hashing-based techniques, rely on what are called pairwise independent hash functions or also two-wise independent hash functions. What are two-wise independent hash functions? Well, we are looking at a family of hash functions over n variables. So the assignment space is 0, 1 to the n to cells that can be mapped by m bits. In such a case, a pairwise or two-wise independent family will ensure that for every pair of assignments over 0, 1 to the n, and for any two cells, if we pick a hash function randomly, then the probability h maps y1 to alpha 1 is equals to the probability h maps y2 to alpha 2, which is 1 over the number of cells. Furthermore, these events are pairwise independent. In particular, probability H maps y1 to alpha 1 and H maps y2 to alpha 2 is the product of marginals. Why is this important? Well, the random variable that we'll be looking at is the number of solutions in a randomly chosen cell. We are partitioning everything into the cells that can be represented by m bits. So we have 2 to the m cells. If we have a pairwise independent hash functions from the family, then it will ensure that in expectation the number of cells solutions in a cell is total number of solutions divided by total number of cells. Furthermore, the variance is small. In particular, variance is upper bounded by expectation. Once we have these two uh, relations, we can use standard concentration bounds to bound G within 1 plus epsilon factor with high enough probability. So where are these pairwise independent hash functions? Let me discuss the standard construction. We have a set of variables x1 to xn. To construct a hash function mapping over the assignments over n variables to cells that can be represented by m bits, we choose m random XOR. How do we choose every XOR? We pick every xi with probability half and we XOR them. So maybe you might pick x1, x3, x6, and so on. In expectation, each of these XORs are going to be of the size n over 2 because you have n variables and you are picking each of these variables with probability half independently. So in expectation, you would expect that there would be half of the variables. To choose a cell randomly, we set each of these XORs to 0 or 1 randomly. So if we pick m XORs, then maybe we set the first one to 0, second one to 1, and so on. Now, going back to our technique, we wanted to choose one of the cell and then enumerate solutions in the cell. A cell can be represented by conjunction of the original formula with these m XOR constraints we have. And well, as we have seen our past 4 days, we have access to really powerful set solvers. So we give out this formula to the set solver and we ask them to enumerate solutions. From theoretical perspective, the problem is almost solved, but in practice, there's more to the story. Turns out the performance of the state-of-art set solvers degrades with increase in the size of XORs. If we want to handle problems involving tens of thousands of variables, then we are going to have XORs of the same order of magnitude, right? In expectation, each of these XORs are just n over 2. And the current set solvers will not be able to handle such large XORs. So remember the observation, set solvers are not set oracles. Just because the query is of polynomial size does not mean that our solvers will be able to solve. So how do we address it? Can we pick variables with probability less than half? In that case, we tend to lose the guarantees of two-wise independence, and then we will be left without any guarantees over estimates we are getting. So how can we address this? The important observation was that do we really require all the variables to specify solution space of the formula? Not really. Consider the formula x3 equals to x1 or x2. In this case, once I give you the assignment to x1 and x2, it uniquely determines the assignment to rest of the variables which is x3 here. Can we try to formalize this concept? So we are going to call a subset of variables. I'm going to denote it by I. It says an independent support if for every pair of solutions of the formula, if two solutions agree on I, then they have to agree on the rest of the variables. So going back to our formula F, we can see x1 and x2 is independent support because once two solutions agree on x1 and x2, they have to agree on x3 since x3 is just x1 or x2. But not every subset of size 2 is an independent support. For example, x1 and x3 is not. Why so? Well, you can assign x1 and x3 both to 1, and at that point, x2 can take value both 0 or 1, right? If x3 is 1, x1 is 1, x2 can be 0 or 1. So if we assign the values to x1 and x3, it does not imply, it does not uniquely determine assignment to rest of the variables. Okay, so going back to the independent support, can it be helpful? Turns out yes, because we can have random XORs only over independent support. Is that going to help us? Yes, because as we see, typically we start with some problem and we encode that into CNF. And during this encoding phase, we introduce lots of auxiliary variables. And all these auxiliary variables that get introduced are dependent. Given a formula, can we figure out what is the independent support of a formula? Yes, we can figure out by reducing this problem to minimal unsatisfiable subset, and that's going to require linear number of calls to NP Oracle. At this point, might wonder, why are we doing something, a problem that we are going to solve, which I'm going to tell you later, requires only logarithmic many calls to the SAT Oracle. Now suddenly I'm telling you we are going to do something that is going to require linearly many calls to NP Oracle, get the quantity, and then we are going to use this independent support in our execution for rest of the algorithm. The reason this makes sense is because the queries that we are making here to determine the independent support are really easy queries. So it pays off to do a linearly number of queries, get an independent support, and construct XORs only over these independent support variables. In fact, in practice, you see that the additional overhead that gets introduced because of computation of independent support really pays off, since it leads to about 2 orders of magnitude runtime improvement in the rest of the algorithm. So this is a design that gets inspired just because the underlying set solvers behave differently for different kind of formulas. Okay, so what we did so far, we start with a formula. We can construct a in small independent support, put XORs only over these variables. How do we solve such formulas? We have sparse XORs, but these are still CNF XOR formulas. What can we do for such formulas? Maybe we can translate XORs to CNF and perform CDCL. Turns out that does not work because for XORs, we know that resolution-based methods have very strong exponential lower bounds, and that does also manifest itself in practice. What else we could do? Well, XORs can be solved by Gaussian elimination. They are just simple linear equations modulo 2. So thankfully, Matheus in 2009 started designing this solver that tries to support CNF XOR formulas natively, and this has been really critical to the performance of these hashing-based techniques. Over last few years, we have focused on improving this solver, and the idea is that we want to perform the CDCL and the Gaussian elimination in tandem, and later on we have discovered that even a tighter integration leads to much better performance improvement. So it is very important here that we have access to a set solver that can support these kind of formulas natively. Okay, so now let me get to the second challenge, which was how many cells do we have to partition into? We want to partition into the number of cells so that all the cells have roughly equal number of solutions. Let's say we want all the cells to have about some threshold, some parameter threshold many solutions. So how many cells do we want to partition into? If you told me the number of solutions, then I know how many cells to partition into. But number of solutions is what I'm trying to estimate here. So that looks like a bit of a catch-22 situation. So let's see how do we resolve it. The idea is kind of very simple. You try for all these values of m from 0, 1, 2, and so on. At every point, you check if the number of solutions is less than the threshold that you have. I'm going to come back to how we very quickly, so hold on to that. Let me first discuss how this process works. We start with the original formula and we ask, hey, is the number of solutions less than equals to threshold? How can we do such a check? We can ask the set solver that or set oracle. If we are just looking from theory, then we are going to ask for the first solution and we can block the solution, and then we can ask for the second solution and so on until we have either found threshold plus one solutions or the set oracle comes back and says the formula is unsatisfiable. So let's say the number of solutions turns out to be we have found threshold plus one solutions. In that case, the answer to this query is no. Then we partition into two cells by just putting one random XOR. We pick one of the cell and we ask the question again. If the answer is still no, we partition into four cells. Again, we have chosen one of them. Keep asking this until we reach a point where the number of solutions is indeed less than equals to threshold. At that point, our estimate is the total number of solutions in this randomly chosen cell multiplied by total number of cells. Let me represent it in the language of formulas. So what are we doing? Initially, we had figured out that the number of solutions of F is greater than threshold. So we put one XOR constraint, right? Q1. Then the second query was to put two XOR constraints. And we kept doing it until we get to the first query that returns the answer yes, which is to say that the number of solutions is less than equals to threshold. And our estimate was the total number of solutions of that formula times 2 to the n. Let's look at these formulas for a minute. Do we see something here? Look at the formula that we construct for query I plus 1. Is essentially the formula at query I, and we added another constraint here. So what does that mean? Number of the set of solutions for query I plus 1 is a subset of the set of solutions of query I. So we know that if query I is going to return yes, then query I plus 1 must return yes, right? If at query I, the number of solutions is less than or equals to threshold, then adding another constraint cannot increase the number of solutions. So instead of doing a linear search, we can do logarithmic search. How many set calls we are going to do? Just the log of the number of log of n. Much more importantly, is that this enables us to do incremental search for most part of the logarithmic search, because you have query I, then when you are adding more constraints, you can still reuse the learn clauses that you had when you solved query I. So that's well and good from practice perspective. Is this going to always work? Are we going to stop at the right value of m that we wanted to stop? Remember, we wanted to partition into the number of cells so that all the cells have about threshold many solutions. So we have an ideal value of m in mind. We called it m star. So are we going to stop close to the M star? Typically, the analysis of this requires us to reason about these queries I and j. These queries are not independent anymore, right? Because the query that you construct for I plus 1 depends on the query that you had for I. So lack of independence might force you to apply union bounds, but thankfully you can make a crucial insight in analysis is that the what can go wrong. One thing that can go wrong with dependence is that you choose some QI and then you are stuck with that QI for rest of the execution. So the probability of making such a bad choice of QI is very small for small I. So the chances of you getting stuck with a bad QI is very small. How does that translate to analysis? What we can say is that the algorithm that I just discussed terminates with value of I'm very close to the ideal value with probability, let's say 0.8. And whenever it terminates very close to the ideal value, then the answer it returns is within the tolerance epsilon with probability 0.8. So you can combine the two. So with probability something of 0.64, you do make sure that um, the answer, the algorithm is getting a good estimate. And now you can repeat it log of 1 by delta times and you can return the median. Okay, so that's how the analysis of these algorithms work. We show that it terminates to the value that you wanted it to, very close to the ideal M star. And when it terminates there, you get the answer with that is correct with probability some 0.8. Let me come back to the one final challenge, which is what exactly this small cell. I kept telling you that I'm going to call a cell to be small if it is about threshold many solutions. What choice of threshold can we have? Well, first observation that goes back to Stockmeyer's work in 1983 was to say that we can have threshold to be a constant. And then you can show if threshold is constant, then you can get a constant factor approximation, say a 4-factor approximation. Suppose I give an algorithm that can compute a 4-factor approximation. Can you turn this into an algorithm that compares a 2-factor approximation? Turns out yes. Let me show you how. Start with a formula f. You make two identical copies of this formula. Let's call them f1 and f2. So now let's look at g. The number of solutions of g is square of the number of solutions of f. Just to make sure. The number of solutions of g is square of the number of solutions of f. So if I give a 4-factor approximation of g, then taking a square root of that would give a 2-factor approximation of f. Yes. The two copies are with different variables. Yes. So if f is over x, then we make another copy with, substitute this with a new fresh set of variables. Okay. So as you can see, we can transform such an algorithm to a 1 plus epsilon factor by making 1 over epsilon many copies, and we can take 1 by epsilon root of the answer. Approach 2 is to say that let's try to have threshold to be large. It can depend on epsilon. So you can typically this kind of dependence comes out to be 1 by epsilon square. So if you have threshold to be 1 by epsilon square, then you can get a 1 plus epsilon approximation directly. Turns out in practice, between these two approaches, approach 2 works much better then approach 1. So approach 1 was to set a threshold to be a constant, while approach 2 was to set threshold to be 1 by epsilon square. If you do the analysis, turns out approach 2 has slightly worse complexity from set oracle perspective, but in practice it works much better because it's much better to work with a small formula and enumerate more solutions rather than make multiple copies of the formula and put XORs over these copies of the formula. So again, this observation that I told you at the start comes back to light, that the performance of the solvers depends on the formulas you give to them. So if you construct a formula by making multiple copies and you want to put XORs over all those variables, that becomes much harder for the underlying solver to solve. So instead of that, it's more advisable that you enumerate more solutions. So instead of having threshold to be a constant, we end up enumerating more solutions, but of a small of the original formula rather than making multiple copies.
Kuldeep, there is a
Yeah.
question by Rupak
Ah,
on the chat.
somehow now I cannot.
Okay, so let me read the question. When you
Okay,
make,
I figured it out.
all right.
Yeah. When you make, is there an advantage? Turns out not much, because when you make multiple copies, then the XORs that you put are between different variables, different copies. So most of the learned clauses that you are going to get are over the variables that are across different copies. So you don't get any advantage actually.
Can I ask a question going back a little bit about independent support? So you made a claim that the number of variables in the independent support is an order of magnitude smaller than the total number of variables, correct?
Yeah.
Is that something that you have empirically verified, or how did
Yes.
you come to that?
We usually get very, very small independent support. So typically, 10 to 100 factor of difference. So 1 by 10, 1% of the variables turned out to be independent support.
Okay.
Okay, so what I just discussed, putting these three together, the algorithm has 1 plus epsilon factor guarantees with confidence 1 minus delta, and we end up making logarithmically many calls to the set oracle with a epsilon square dependence. What is also nice about the scheme that I just talked about is that if the original formula is DNF, then each of these queries that we had, right, which was to figure out is the number of solutions less than equals to threshold, that turned out to be polynomial time. So if it original formula is in DNF, then these hashing based techniques give rise to an FPRAS, which is different from the Monte Carlo based FPRAS known for DNF formulas. Turns out this new FPRAS also works well in practice. Okay, so let me now try to showcase that all these improvements over the years have been also translating into practice. So here are I just picked approximately the counter that we have been working on over the last 5 years. The improvement in approximately, these are on x-axis is the set of benchmarks, on y-axis is the time. So these are the cactus plot. And as you can see, we would ideally like to go to right as much as possible. So over the past few years, we have seen that different versions of approximately has really improved in the ability to scale to large instances. Okay, so far I talked about counting. I introduced the hashing based framework. Now let me get into the second half of the talk, which will be talking about sampling. So the problem of sampling, just to remind, we have a set of constraints over the variables x1 to xn. A uniform sampler would ensure that the probability a solution is output is 1 over the number of solutions.
There's a question by Sybil. Need not the disjuncts in the DNF be pairwise contradicting?
maybe I can come to it later. Just to, yeah, there is a
Sure.
small argument that one needs to give why this would be polynomial time. So probably we can take it after the talk.
Sounds good.
Yeah, that's a very good question, and there's a small argument one needs to give there. So going back, I was talking about uniform sampling. What we want to do in uniform sampling is to make sure we sample a solution with probability 1 over the number of solutions. We'll be fine with an almost uniform sampler where the probability is within 1 plus epsilon factor of the ideal uniform probability. Turns out counting and sampling are closely related. By the seminal work of Jerome Valent and Vajrani, we know that approximate counting and almost uniform sampling are interreducible. Now that we have a powerful counter, one idea would be let's go to the reduction and use it to design a powerful sampler. But the reduction doesn't turn out to be efficient in practice because the sampler requires linear number of approximate counting calls. Remember, we were not fine with linear number of calls to the set solver. You have been with me all this while, so there's no going back. Calling the counter linear number of times is not going to work. Well, we can go back to our hashing based approach. If we have partition into the space of solutions into cells that are roughly equal, then why not just pick a random cell? We check if it is small. In that case, we have enumerated all the solutions and we are going to pick one of the solutions randomly from this randomly picked cell. Is this going to work? What things do we have to answer? How many cells should we partition into? You know the drill. If we knew the exact count, we would have figured out how many XORs to put. But we have an approximate counter. An approximate counter gives epsilon approximation of the count. In that case, let's get the approximate estimate from approxMC. From there, we can figure out how many XORs to put. Since this is an approximation, so we'll have to deal with +1 -1, right? So let's look in the range. I just want to also highlight how the arguments work here. What we have to argue is that the probability we output a solution is going to be probability we choose the solution from the cell. Since all the cells have roughly threshold many solutions, so this is, you can bound by a constant. And then probability the cell is small given that the solution that we want is in the cell. And this conditioning leads us to require 3-wise independence instead of 2-wise independence in case of sampling. I'll come back to the issue about 3-wise independence. But before that, I just want to point out the scheme that I just introduced will ensure that we can output a solution within 1 plus epsilon factor of the ideal uniform probability. Furthermore, how many calls to the counter we are making? Just one, right? All we wanted to do was to figure out how many solutions the formula has. So this improves quite a bit from the linear number of calls that you would have to require if you were using the reduction from counting to sampling. But there is a catch. The earlier algorithm could work with just 2-wise independent hash functions. The scheme that I just introduced, we call it Unigen, requires 3-wise independent hash functions. Fortunately, the random XORs are 3-wise independent, so nothing has to change. We can continue using the random XORs. Does this work in practice? Let me try to convince you. And this will be a good check for those of you having early morning. So here is what we did. We took one of the benchmark. We knew the set of the number of solutions, so we could output all the solutions and we could simulate a uniform sampler, which is if you know all the solutions, you can just pick one of them and repeat it. We repeated 4 million times. So one of the plot is from the ideal uniform sampler and another is from the scheme that I just introduced. Perhaps it's easy to figure out which one corresponds to Unisen versus which one corresponds to the ideal sampler. But if you are having hard time, don't worry. The two are statistically indistinguishable. This is an observation that we have been having over past few years consistently for all such benchmarks where we have done such studies. Of course, these kind of studies you can do only for the formula that have small number of solutions. Let me take this opportunity now to conclude the talk. I started I motivated a study on sampling and counting by arguing that now that set is easy, again, it was in courts, we should look beyond satisfiability. I discussed hashing based techniques for counting and sampling. One of the things that we have seen for both counting and sampling over past few years, there are a lot of improvements in the underlying algorithm, this underlying solvers that solve the CNF XOR formulas. And these work has led to improvement in the performance of the counters and samplers. Where do we go from here? Well, I think this is just the start of what we can accomplish for counting and sampling. Ideally, we would like to scale to much larger instances than we can do right now. How do we get there? One, we would require some challenge problems. Here are some challenge problems based on the application of this counting and sampling. In case of, there are applications of counting to estimate reliability of power transmission grids. So ideally, if we could have reliability of a city of the size of Los Angeles, that would be a good challenge. Or to estimate the leakage. Right now, you can use counters to estimate leakage of C++ programs with few tens of lines of code. It would be nice if we can, the challenge that I would like to suggest is to try to handle problems involving about 1,000 lines of code. And similarly, in case of sampling, one of the application of sampling is in hardware verification, where you want to test, to use the samplers to design, to sample the test cases. And right now we can handle problems that have about few hundreds of SMT nodes. It would be nice if we can extend another order of magnitude. How do we get there? I'll try to sketch few directions. One of them, in my view, is a tighter integration between solvers and algorithms, designing algorithms based on what the solvers can do, and also designing solvers, because these algorithms make a structured set of queries, so you can, a tight integration is going to pay off. Something that I did not discuss a lot was that, well, instead of just uniform sampling, you might also want to have some distribution of solutions. The counting problem becomes that of integration, and there is a lot more that needs to be done to lift these techniques to weighted distributions. In case of SET, one of the things that was very has been very influential in the last few years is to be able to verify or test when the set solvers are returning unset. Then there's has been a lot of work in coming up with techniques that can verify that the unset answer by the solver is indeed correct, because it has to output the proof in certain format. We need to work on similar questions in context of sampling and counting. How do you know that the count that was written by the approximate counter is correct? How do we know that the distribution that we are generating is indeed close to the ideal distribution that we would like to have? So with that, I would like to conclude. I'll be very happy to take any questions now or later during the break. Thank you everyone for being a wonderful audience. I will be around.
Thank you, Kuldeep, for a great talk. Thank you. Okay, questions, please. Either type it in the chat or unmute if you can, or the Q&A. So there's a question by Jan Kefir. It seems that your methods rely heavily on XOR plus CNF solving. Do you think it's probably that XOR plus CNF SAT solving could be proven as hard as SAT counting sampling? By, for example, by quantifying over the number of XORs.
So, um, I don't know. Is the question that just finding a solution to CNF XOR that can be proven? I cannot see the
Probably, yeah.
question, by the way.
Yeah, it's on the Q&A.
Ah,
You have
okay.
to.
Ah, yes.
Can you see it?
Yes, I can see. I don't think that it would be as hard as counting or sampling. Um, I mean, in theory, certainly this would require a lot of assumptions to break, but in practice also, um, it doesn't look like that it is as hard as doing the queries. But one thing that is important that and would be worth highlighting is the most amount of time that is spent by the solver is indeed for the last query. So just when you get to the last, so we are going to do two queries, right? The first query that returns yes, and the query just before that that returns no. These are the two queries that end up taking most of the time. So it would be interesting if we can show some sort of results about hardness of these two queries. Um, one could try to look at that these queries are close to what would be similar to phase transition region. But again, the formula that we start with is not a random formula. So these are structured instances. We have done some work looking at random formulas. When you have random CNF and random XORs, then you can look at the phase transition behavior. But of course, those results don't tell us a lot more much about what's going on for structured CNF instances.
Okay, a couple of questions from Ciaran McCreesh. I hope I'm pronouncing your name correctly. My apologies if I'm not. Do you have any idea what proof logging for approximate counting would look like, or even for exact counting when you're doing something beyond listing all solutions and then proving there aren't any other?
I guess, yeah. So work from Kiran and Jakob. We would need to log answers to the CNF XR formulas. One would need to do, I think that gets into an interesting question, which is how do we verify the randomness here? So probably we are going to assume that the randomness source modulo that we are able to generate these random bits. The rest of the logging has to be about logging the answers for CNF XOR formulas. So the recent work that I believe appeared at AAAI would be very interesting.
So there's a comment by
For
Ryan. Sorry, go ahead.
yeah.
Okay, there's a comment by Ryan Williams answering Jan's question, and the comment is, in terms of complexity, it is not possible for XOR plus CNF SAT to be as hard as counting SAT unless, for example, P to the sharp P is in NP. Okay. There is another question by Yarko Savela. Your cactus plots show how the performance of ApproxMC and Unigen have improved drastically. What sort of changes were made to the programs to improve performance so much?
So the changes have been, I'm going to discuss some of these in longer talk on 9th of February. So both algorithmic and improvement in the underlying solver. So both have contributed. So I'm going to discuss each of the algorithmic changes, for example, finding independent support, um, uh, being able to generate sparse XORs even further, how they affect, and also designing better underlying solver, CNF XOR solver that we have been doing for last 2 years on tighter integration that goes via framework of recovering of XORs and destroying them and so on. So the improvements have been both algorithmic and the system level improvements. So probably I'll defer that to talk on 9th, since I'm going to discuss those in more detail.
Okay. And there's a question by Laurent Simon. Hi, Laurent. What about counting the prime implicants or minimal solutions?
Yes, so we have a work last year on counting the number of minimal unsatisfiable subsets, both in approximate and exact. We've done some work trying to lift these algorithms. Of course, that turned out to be much harder problem, and a lot more that needs to be done. But the same hashing based idea can be lifted there. We are not able to take advantage of the fact that the only solution that we have to look at are minimal. So that would be nice if we can take advantage of that, either in coming up with the XOR, the hash functions, or in terms of solving.
Okay. Thank you, Kuldeep, for a fantastic talk and a lot of interesting discussion. Thank you very much.
Thank you.
So Jakub posted a note saying next Tuesday, February 9th at 5:30 p.m. CET, Kuldeep will give a more in-depth talk on this topic in the Beyond Satisfiability Workshop Seminar Series. Not sure whether this has been officially announced yet. Okay. All right. We're going to take a short break, say 5 minutes.
There was a question also, I think, or did we already answer that by Oded?
Oh, I don't see it. Sorry.
Is there any way to use the internals of CDCL to estimate number of solutions? For instance, if the CDCL had to do a lot of backtracking before finding a solution, it may suggest that there are few solutions.
Yes, so we have been doing some work on this, and I mean, this is a heuristic that works pretty well in lots of cases. So it does turn out that based on how CDCL has been doing, I mean, we had to also estimate some other quantities along the way, but you could get a good estimate of the number of solutions for a lot of cases. Of course, there are fairly benchmarks, what we could call real world benchmarks, where these kind of heuristics will give very off answers. But this can be used as a good way of getting a good guess estimate that can be verified later on, because that can give us information about how many XORs we have to try out.
Thank you, Kuldeep. Sorry, Oded, for missing your question, and thanks, Jakub. How about we take a 5-minute break and reconvene at 12:35 EST, or 5 minutes after. Okay. Thank you very much.